So I can be. So this one.
I'm holding cis 1,2-dibromocyclopentane and trans 1,2-dichlorocyclopentane. True or false? These are enantiomers.
False.
What are they?
The other one.
Yeah.
I don't know what that is. The other one.
Diastereomers.
That's the word.
So let's just draw these out. Now I need to draw one just like this. It's a mirror image. What do we call that?
Stereo.
It is a stereoisomer, but these are also stereoisomers. What's the name of?
Enantiomers.
Right, enantiomers. That's not a very good reflection. We don't care. And we could probably even give this a little 3D pizzazz, you know? If I look at this one here, the bromines are coming out at me, right? So are the hydrogens. They'll be warm up to what a Fisher projection almost might be. So what do we want to do? I probably want to make that number 1, this number 4, this carbon over here number 2, this one over here number 3. So I kind of like the hand method. If I put my thumb going out, because I got hydrogen going out, I can see I have the wrong hand. All like this. Here's my thumb coming out towards the hydrogen, and I curl from number 1 to number 2 around to number 3. 1, 2, 3. Looks like I'm turning the car to the left. The steering column's in the wrong position. I'm turning it like this. Here I'm turning it to the right. All right, so 1, 2, 3. This must be R. Now we'll get rid of these. Bromine's going to be number 1. This one's going to be number 2. This is number 3. Thumb going out over to number 2. This hand's got number 3. So that's my left hand. Interesting. This is an R and S. All right. Good enough. I'm going to come over to this one and I'm going to say, okay, let me just find it with the model kit. That's this one here. Put my thumb where the hydrogen is. Doesn't look like I'm wrapping around the right way. It's good to go walk through. Alright, now it's making sense. Here's my drawing. Here's the bromine. Here's the hydrogen. Put my thumb in the direction of the hydrogen. This is number 1. This is number 2. This is number 3. So I'm curling around. I got my left hand. So that is S. And it might make kind of sense over here. We did this correctly and we say this carbon is R. If we flip these, it needs to be the opposite. Because over here, this still has higher priority than this one over here. So let's just figure this out. This was 1, this was 2, this was 3. I had to use this hand to go bromine to this one, to that one. Now if we trust our work, well, look at here, this bromine is in the same position. I think it better be S, right? Let's just figure it out. This is going to be 1. This here's going to be 2. This thing here is going to be 3. Thumb pointing out where the hydrogen is. I'm going to wrap it around 1, 2, 3 like this. Check it out with the model. Point my thumb out because hydrogen's out. Here's my number 1, my number 2, around to my number 3. So these are both SS, and if I trust my work, I'm probably just going to say this must be R, R. I got my model. If I trust my work, I'm going to just grab my right hand. Thumb's coming out. All right, so there's number 1, number 2, number 3. 1, 2, 3 on the priority. 1, 2, 3. 4 groups here connected to that asymmetric right hand. Thumb out. 1, 2, 3. That looks like R. Bromine's going up. Let me get my right hand. Put my hand in the direction of the hydrogen. And we can see my hand's going to go first priority, second priority, third priority. So the cis is RS. The trans, we have 2 enantiomers. One is SS and one is R. All very interesting. Let's talk about the property of enantiomers. These 2 trans, 1,2-dibromocyclopentane, they're going to have, if I have a bottle of this one and a bottle of that one, they're going to have the same boiling point, the same melting point and density, same refractive index. What's that?
How much they reflect light?
Kind of been like you think about a lens refracting light. It has to do with the speed of light in that material. We don't need to know that so much. And then this thing, rotate the plane of polarized light in the same magnitude but the opposite direction. We haven't talked about that, but we're going to talk about that here in a second. Find out what that means. Here's the exciting part. Different interaction with other chiral molecules. Active sites of enzymes are stereospecific. We looked at amino acids in your body. They're all called the L form or left-handed. So taste buds and scent receptors are also chiral. And the enantiomers have different smells. So here's something interesting. How many of you like rye bread with lots of caraway seeds in it? How many of you have no clue what I'm talking about? See, when I was a kid, they brought home rye bread and it had caraway seeds, and it was like the most disgusting thing. And it wasn't until an adult I found that you can buy rye bread that doesn't have any caraway seeds in it, and it's just made with more grain from grain rye. All right, how many of you like spearmint gum? Spearmint is a molecule, and its mirror image is what gives rye bread its taste. But unfortunately, nobody knows what I'm talking about with that rye bread caraway seed taste. So here's what is this? Epinephrine. Is there any other names for that? I wonder why would your body make epinephrine? I think it's like a flight or a fight molecule. I think it has a common name called adrenaline. That's why I go bungee cord jumping. So look, this has R. We could probably figure that out. So here is a mirror image of that thing, and that is not going to fit into the active site on an enzyme. So when we have a mixture of the two enantiomers, we have what's called a racemic mixture. A racemic mixture has both enantiomers. So here's a 4-carbon chain. And we have this oxidized carbon at carbon number 2. We have a ketone. We can reduce the ketone to an alcohol with hydrogen, and I would call it a syn addition of it. Hydrogen adds to one side of this thing. And you could probably tell me this thing was flat and planar because this carbon is sp2 hydride. So if the hydrogen adds to the top, we get this alcohol. This would be R2-butanol. Makes sense to me. If it adds to the bottom, we would have S2-butanol. So here is one way man goes into the lab and makes something, and he doesn't do as good a job as nature, because nature makes just one enantiomer. So back in the 60s, chemists came up with this drug called Thalidomide. It was widely used in the late 50s and early 60s for the treatment of nausea in pregnant women. And it became apparent in the 60s that thalidomide treatment resulted in severe birth defects in thousands of children. A horror, just a horrible thing that happened. And we see here 2 enantiomers. It says the S enantiomer is the famous, it should be infamous, not famous, the infamous enantiomer that caused birth defects. The R enantiomer has a sedative effect, while the S enantiomer is teratogenic. Exactly that. So I put up the online homework for chapter 5, and it said you should only take about a half hour to do 10 questions. I did them all. I found one error, but we're not going to worry about it. And they had a weird question. They should say which molecule has a achiral center or achiral carbon. The words is weird with which of the following have a mirror image. So where are the achiral carbons? You can probably focus on here is a wedge. Here's a dashed wedge. So this thing is coming up. This one's going down. An achiral carbon has 4 different groups. It is right there. There's your achiral. There's your asymmetric. I don't want to mix that all up. Asymmetric and chiral mean the same thing. So this relieves nausea in pregnant women, has a nice sedative effect. This causes birth defects. So let's talk about polarized light. Any of you have polarized sunglasses? They help take the glare off things, and you can see through windshields better sometimes. What is polarized light? Well, there's what we call plain polarized light. Here's something that has little slits in it. It says here, plain polarized light is composed of waves that vibrate only in one plane. So it doesn't bulb. It probably has multiple wavelengths. But in physics, you might learn about a magnetic field and electric field that are perpendicular to each other and they're propagating along. So just choose one of those to go through a slit. I don't know if it's the electric wave or the magnetic wave, doesn't matter. You hear light is vibrating in all directions. When it comes out, it's only letting one that's vibrating in this way, multiple photons all going through there. So now we have what's known as plain polarized light. So you put in an enantiomer here. And it says here, enantiomers rotate the plane of polarized light in opposite directions, but in the same number of degrees. So if we just have one enantiomer, not a racemic mixture, we put it in the sample cell, turn on this light, and notice we have little slits just like this one. We turn this thing around until it lights up. Because as this plain polarized light goes through the enantiomer, it gets rotated. We turn this analyzing filter and it tells us how much it gets rotated. We call this device a polarimeter. And if you look in a chemical catalog, you can buy the L form or the D form of like a particular enantiomer. The D form is the dextrorotatory, L form is the levo, and I said the amino acids are all in the L form. Now, unfortunately, you can have an enantiomer that rotates light to the left, and we call it levorotatory, and it could be R, it could be S. So our designation here for R and S enantiomers is what we do on a paper to differentiate, but nature does its own thing. So maybe there should be a little asterisk here. These are related to the stereogenic center, but nature wasn't kind and said everything that's dextro is R and everything that's levo is S. Doesn't work out that way. Changes from molecule to molecule. So this would involve math, specific rotation, depends on the length of the cell and contraption, as well as the strength of the optical activity, temperature, and wavelength of light. So these are normally tabulated out, where C is the concentration in grams per mil, and L is the sample length. So in the chemical catalog, sometimes it will give the information. So here's our 2 enantiomers and 2 butanol. And if we have a racemic mixture and we put it in the polarimeter, it doesn't rotate the light at all because they cancel each other out. Each enantiomer cancels it out. Equal quantities of the D and L enantiomers kills optical activity. And then the mixture may have a different boiling point than the pure enantiomers by themselves. So there's a few weird things out there that have optical activity. What does that mean, optical activity? That means you can rotate polarized light. We might even figure out there must be some stereochemistry going on. So if we look here, we're not going to find any carbon with 4 different groups. But this molecule has a mirror image. There it is. And they're non-superimposable. And that's because they can't rotate, so they're in a fixed position. The staggered conformations are chiral. They're non-superimposable mirror image. Here's another crazy one, allenes. We'll see what an allene is in a second. Some allenes are chiral, even though they do not have a chiral carbon. The center carbon is sp hybridized. To be chiral, the groups at the ends of the carbons must have different groups. So this thing here, this is an alene. It has this sp hybridized carbon in the middle, and these are sp2. And so none of this can rotate, and it locks these in place. So if you have a model kit and built these, and maybe you can see it here if you imagine swinging this thing around. See, these are in the plane of the board. You swing this around, these would line up, but this thing that's coming out would be going behind, and this thing that's going behind would be coming out. So these are non-superimposable mirror images. Any questions?